We can now check our results to ensure that our simulation makes sense. We will first look at expected trends to validate that we solved the correct mathematical model, and then verify our results by investigating whether we solved the selected mathematical model correctly. First, we can take another look at the mass flow rates calculated in the solution process. While we do not have exact experimental data, we can use the flow descriptions from textbooks to help validate our solution. In literature, as mentioned in pre-analysis, we can find that the flow in the internal and external carotid arteries should be approximately 70% and 30% of the total flow in the common carotid artery. Using these mass flow rates to derive percentages, we get that 70.2% of the flow leaves through outlet 1, while 29.8% leaves through outlet 2. This is very close to the values from literature and helps to validate our solution results. Next, we can work to verify our results by first performing some sanity checks and ensuring that our boundary conditions are satisfied. Looking at the velocity contours, we can see that the inlet velocity matches our assigned value of 0.315 meters per second. Similarly, in the pressure contour plot, we can see that the outlet pressures match the assigned gauge values of 0 pascals. This demonstrates that our inlet and outlet boundary conditions are satisfied. In the velocity contour plot, we can also see that the no slip and no penetration boundary conditions at the wall are satisfied because the velocity magnitude near the edges of our plot are nearly 0. This shows that all boundary conditions were satisfied as expected. Next, we can work to determine and reduce the numerical errors in our solution process. To start, we can again look at the mass flow rate report shown previously. As mentioned in the numerical results video, this net results value shows the difference between the calculated mass flow rate entering the artery and the mass flow rate leaving the artery. We can see that this value is extremely small. This is a good indication that our solution has converged and that the overall errors are small. We can reduce the numerical errors in our solution process in two ways. Firstly, the convergence criteria can be reduced so that the solver runs for more iterations. This reduces the linearization error and will help the results to converge. This can be accomplished by changing the residual value at which the iterations stop to a smaller number. Secondly, the mesh can be refined to contain more elements. This means that the solver will find values of the primary unknowns at more points in the flow domain, and the discretization error will be reduced. This can be easily achieved by reducing the element sizes in the meshing step. Since our convergence criteria was already fairly small, this is likely to have a larger effect in reducing errors. We can expect the largest changes to be seen on the wall shear plot, since it is highly sensitive to the mesh near the outer boundary. Here's an example of a refined mesh. This was created by halving the element size for all of the body sizings and doubling the number of layers in the inflation. This leads to nearly 5 times the number of elements. This is likely overkill, but it serves as a basis for more careful refinement. I encourage you to go through these steps by yourself to verify and improve the solution process.